Today I'm gonna talk about more in-depth concept of p-n junction. Uh, so in the last video, uh, maybe I'm wrong but I've talked about some p-n junction concepts. So when we apply or when we combine p-type and n-type semiconductor, we can make the p-n junction. So when it is a state of thermal equilibrium state, we have the Fermi level has to be a constant line, making the energy band like this, and we have to know that the curvature of energy band here is actually the electric field, and I'll tell you why now. So when the n-type and p-type are combined, because of the difference of the amount of electron and holes in each side, the diffusion occurs. So for the electrons, because of the diffusion, electrons move from the left side to the right side and making a recombination with the acceptors in the p-type, and just like that, holes in the p-type moves to the n-type, making a recombination with the donors in the n-type. And when the diffusion occurs, both n-type and p-type makes the empty space. I drew like a green line here because the holes and electrons are moved. So for the n-type, the empty space is actually plus fixed charge, because there is only remaining the donors. And for the p-type, it is a minus fixed charge, because there is only acceptors remaining. And because it is plus and minus fixed charge, it makes a electric field. In this case, from the left side to the right side, and we call this electric field the built-in electric field, which is very important. Yeah. So and this is something that makes the energy band curve. It curves until the electrons in the n-type can't move to the side, to the p-type, because the built-in electric field works as an energy band, like an energy barrier that we've learned about before. So the electrons can't move toward the p-type. Yeah. And when it occurs, the charge density, especially for the curve region, this region, the charge density of the left side is the Q times n donor, which is just the amount of donor times the charge plus charge. And just like that, for the p-type, it is minus Q times the amount of acceptor. And for the mobile carrier, because this curvature region is actually charge fixed, there is no carrier, and we call this region a depleted region, which has no carriers in it. So how about we apply a voltage to this PN junction? We have the forward bias and reverse bias, and applying the voltage actually means that it is not the thermal equilibrium state anymore, and the every voltage applied in the PN junction only affects in the depletion region, which means that it only affects on the built-in electric field, built-in potential, which is the VI. It is very important when we calculate the formulas later. So for the forward bias, which the voltage is plus, the energy band gets lower, making the electrons move easier to move to the side, which eventually makes the current flow more efficiently. And for the reverse bias, it makes the energy band more stiffer, which makes the electrons hard to move to the side, making the current stop. So like I said before, the applied voltage only affects on the built-in potential. So for the forward bias, because the applied voltage affects on the Fermi level, for the forward bias, the energy band is the built-in potential minus the Fermi level, the Fermi energy changed by the applied voltage. And for the reverse bias, it is the built-in potential plus the Fermi energy changed by the reverse bias, applied reverse voltage. And let's talk about some effects caused by forward and reverse bias. So first off, is the width. We can just say the width is this part, and for the reverse bias is that part. So we can easily see in the picture that when it is reverse bias, it's wider than before, and when it's a forward bias, it's actually smaller than before. And it is because when the reverse bias is applied, the electrons and holes in the each N and P type tends to move in the opposite direction, and when it is a forward bias, they tend to move closer. So that is why the width changes. And just like that, the current density, the charge density, when it is a reverse bias, it gets bigger, and when it is a forward bias, it gets smaller. And same as the electric field, when it is a reverse bias, it's bigger. And for the potential energy, just like I said, when it is a reverse bias, it is more steeper, so the potential energy gets bigger. And all these can be explained by the picture of energy band here. For example, in the part of electric field, because I said before the electric field is the curvature of the deflated region. You can easily see that when it is a reverse bias, it is more stiffer, which means it's a bigger. And yeah, that's all for today's video.